All right, today let's take a look at topics 1.10 and 1.11, and that's the idea of discontinuities, and I suppose we could say, what is continuity? All right, we're going to take a look at that, and probably one of our best ways to do that is to look at functions that are not continuous. All right, and so we have some examples here on this first slide of functions that are not continuous. We've already seen some of these. We've already seen B and C. All right, we have said in those two situations that the limit on both of these, on both B and C, the limit would not exist as we approach 5. But that also means that it's not continuous. These are called a jump discontinuity. And no, you do not have to write out the word discontinuity every time in your notes, but you do need to be familiar with that word. B and C are what we call a jump discontinuity for obvious reasons. Can everybody see that the function is jumping from one place to another? All right, that one's one of the easiest ones to recognize. Letter A is what we call an infinite discontinuity. That one is also not continuous at 5. It does look like both sides are approaching infinity, but it's not continuous. And letter D, when we look at letter D, yes, the limit would exist, right? The limit as x approaches 5 would exist, but it's not continuous at 5. We could, if I were somehow able to take this and fill it in there, wouldn't it now be continuous? So this one is called a removable discontinuity because it is conceivable that we could fill the hole to make it continuous. All right? So that gets us started with different kinds of discontinuities. Let's take a look at this first situation. We're told that the limit as x approaches 5, and in my template, this did not make it to the template. We're told that the limit as x approaches 5 exists. So these are the ones we just looked at, and then this is just kind of summarizing what we just said. The only one that has a limit as x approaches 5 is D. All right? The others do not have a limit. Let's take a look at another one. Which of the following is or are continuous on the, let's underline this key word again, domain? This problem becomes a little bit sneaky if you don't pay attention to the word domain. Remember, domain is the places where it's defined. So for example, letter A. Now, it's not defined at 5, is it? It's not defined at 5. Well, 5 isn't in the domain, is it? If I were to say the domain of letter A, I would say that its domain is negative infinity to 5, union 5 to infinity. We did that in pre-calculus. We should be able to describe the domain. Well, everywhere that it exists, it's continuous. Right? Look at this. Everywhere that this thing exists, it is continuous. All right, so letter A is one of our choices. All right. Now letter B would be a no, because it is defined at 5. Okay? It is defined, but it's defined at this screwy little point up here. All right? That one is not continuous on its domain. Letter C is continuous on its domain. Notice, it is not defined at 5. And everywhere else that it is defined, it is continuous. And letter D would also be a no, because it is defined everywhere, but we've got this little situation right here. It is defined everywhere. And this leads us to what is called the classic three-point definition. All right? This is, some people call it the three-point definition for continuity. If a function is continuous at a point, a function is continuous at a point C if we must have all three. All right? We must have all three. We must have all three. Number one, f of C is defined. Now, let's go back for a minute. On this last situation here, letter D, f of 5 is defined, isn't it? It's defined as this little point right here. But let's go to point 2. The limit as x approaches C exists. That also has to be the case. Let's go back to our letter D again. Does the limit as x approach 5 exist? It sure does. Ooh, it's looking like this one could be continuous. It has 2 of the 3. What's the third one? Does the limit as x approaches C equal f of C? Let's look at our picture again. The limit of this function would be whatever this y value is over here. Let's say it's 1. And let's say that this up here is 3. Well, the limit as x approaches 5 is 1, but f of 5 is 3. So that's why letter D is not continuous. It fails at the third point. So somewhere on this page, we should draw 2 examples. Here's the first one. Here's C. That one is continuous. All right, this one is most definitely continuous, because it meets all 3 criteria. F of C is defined. The limit as x approaches C exists, and the limit is the same thing as the function value there. All right? But if we add, let's just make a little quick sketch here for the sake of your notes. If I have this one is not continuous. It meets 2 out of the 3. But 2 out of 3 is not enough. All right? Now, one thing we should probably go back and clarify is from this last question. This question was asking something different than what we just talked about. It was asking which functions are continuous on their domain. Letter C is definitely not continuous at 5. Not at 5. But if I were to come over here to like -1, it is continuous. All right, so let's make sure that you read the questions carefully and pay attention to what they're asking. This one is asking on its domain. Let's look at this first example problem. So they give us, you just need to be prepared. A lot of times they're going to be piecewise functions. All right, let f be the function defined above. For what value of k is continuous at x equals 3? All right. So we know enough up here that I can factor this thing. All right. And I can turn it into x plus 3 times x minus 3. And on the bottom, I can pull out an x, and I have x times x minus 3. From our pre-calculus training, we know that anytime I have this and this, there is a hole at x equals 3. So what we want to do is fill the hole because we want it to be continuous. All right? So, what do? Well, this function acts like the simplified version over there. If we were to look at this on the graphing calculator, the function would act like x plus 3 over x. It would act like this simplified version right there. All right? So, let's plug in 3. Let's fill the hole. F of 3 is 3 plus 3 over 3, which is 2. All right? So that means this k value, all right, this is a specific constant value. That means that k has to be 2. All right? What they're doing is they're giving us this deal. Here's 3, and I'm not sure exactly what this function looks like. It's probably going to act a lot like a constant function, all right? Whatever that is. But we've got this deal going on, and we've got this k floating around out here. We've got this k floating around. So what we want to do is we want to fill the hole. And if we make k be equal to 2, then it meets all 3. If k equals 2, it meets all 3 conditions. All right, we're not going to worry too much about what the function looks like at this point. I just want you to see that if we fill the hole, we meet all 3 criteria. All right, let's look at another one. Now this one, of course, looks a lot uglier, but we actually have the skills in our toolbox to deal with it. It's the same type of problem, all right? It's actually very similar. but we've got some algebraic manipulation we've got to do. If I take the square root of 7 minus 2x minus the square root of 7 over x, and I multiply the top and bottom by the conjugate, our good old-fashioned friend, the conjugate. 7 minus 2x plus the square root of 7 over square, same thing here. All right. What we get when I do that, of course, we've got a difference of two squares going on up here. I have 7 minus 2x minus 7 over x times that thing, this deal right here. And so the 7's go away. And I have negative 2x over the x times this deal up here, which is, I'll go ahead and write it in there this time. And we can now factor out those x's. All right? And I'm left with negative 2 over the square root of 7 minus 2x plus the square root of 7. And now we can try to fill the hole. How do we fill the hole? Find f of 0, because that's what we're going to. All right? So f of 0, we're going to plug into this. And I have negative 2 over the square, if I put a 0 in right there, that's just going to be the square root of 7 plus the square root of 7. So I'm going to have negative 2 over 2 square roots of 7. So that's going to be negative 1 over the square root of 7. And that would be my k value. That would be what we're working towards. All right? So, you know, I just want to finish with the question, what do I look for to find where a function is not continuous? All right, you might want to add that. What do I look for if it is not continuous? All right, if it's not continuous, it's going to fail at one of those 3 points. All right? Use your 3-point definition. All right? Use your 3-point definition. Also, look for jump infinite and removable situations, because those are all discontinuities. All right? And we will stop there for today.